Hello everyone. Today I'd like to tell you about some work we've been doing at NIST in the group of Liz Donnelly and John Kitching to study the point source atom interferometry technique. And in particular, I'd like to tell you some of the things we've learned about what goes wrong when you try to do this detection method with a cloud that has a large initial size. But first I want to talk a little bit about the motivation that we have for studying atom interferometry. And of course there's a number of reasons why people are interested in these systems. But our perspective is that we're interested in them because they provide really precise sensors of rotations and accelerations. And in particular, there's been an idea for a long time that these sensors could be used for practical measurements for inertial navigation. And one of the problems with that is that these systems tend to be fairly large, laboratory scale systems. And so to use them in practical applications, you'd really like to point a shrink ray at them. But as these guys in this cartoon that I really love found out, sometimes when you point a shrink ray at things, things go wrong. And so you need to think carefully about what's going to happen when you shrink these systems down. And usually one of the things that goes wrong is that they become less sensitive as you reduce them in size. And so there's an intrinsic trade-off between size and sensitivity. So one of the sort of paradigms for what we're trying to do here is the chip-scale atomic clock, which was developed a number of years ago. And there, the small clocks clearly have less sensitivity than the large systems, but they're smaller and lower power, and that opens up new and interesting applications. So in the rest of the talk, I'd like to give a quick introduction to light pulse atom interferometry, and then describe the point source atom interferometry technique. And then I'll discuss some of the effects that we've discovered the initial distribution of the atoms has on these spatial fringe patterns that we're trying to measure. So I think most of you are probably fairly familiar with atom interferometry. The key idea is that we're trying to use laser pulses to create superposition states with different momenta, and then we can split the atomic wave packet and redirect it and do another beam splitter to create interferometer geometries. So in our case, we're using stimulated Raman transitions. We're using the pi/2, pi/2 pulse technique. So we do a first beam splitter pulse. The two parts of the wave packet separate. We do a pi pulse to exchange the two parts of the superposition. And then we do a final pi/2 pulse to close the interferometer. And then we detect the phase of the interferometer by measuring the transition probability after this interferometer sequence. So what we're looking for are fringes and the state of the atoms after the interferometer, and from that we try to infer information about the rotations and accelerations of the interferometer. Of course, if you're going to detect a phase shift, I have to tell you what those are, and the two phase shifts we're trying to detect are on the upper left corner of my slide here. And there's a few things I want to point out. First is the acceleration phase shift tells you you're sensitive to accelerations along your interrogation axis, along the direction that you kick the atoms. The second thing is the rotation phase shift gives you sensitivity to the two components of the rotation vector that are orthogonal to your interrogation axis. Of course, both of these phase shifts scale very strongly with the interrogation time t, and that leads to this trade-off between size and sensitivity. The final thing I want to point out is that we want to detect both of these phase shifts in the same experiment, but that means that you need to have some way to tell them apart. And the way that that's been done traditionally is by exploiting this velocity dependence. Typically what people have done is use multiple atomic sources with atoms going in opposite directions. And here I've got some cartoons of the different geometries that have been used. The first successful light pulse atom interferometers were based on thermal beams. So you have counter-propagating thermal beams, you get two phase shifts, and you can distinguish these two contributions. And in the last decade or so, there's been a lot of work on cold atom systems where you make multiple magnetoelectric traps and you launch them towards each other to get your counter-propagating atoms. So these systems have been very successful, but they're still relatively large and relatively complicated. And so we've been interested in a new technique that offers a way to distinguish these two phase shifts with a single cloud of atoms. And that's the technique that's been called point source atom interferometry by Mark Kasovich's group. So to see how it works, imagine that you've got a small cloud of atoms that contains a range of initial velocities. Ideally, the cloud would be infinitely small. It would be a point source in space. And then at the beginning of your experiment, you let the cloud start to expand. And as the cloud's expanding, you apply your sequence of pi/2, pi/2 pulses. The key idea here is that the cloud expansion is creating correlations between position and velocity. You can imagine that if all the atoms initially started at the same position, the final position of each atom is just going to be determined by its initial velocity and the expansion time. So this velocity-dependent rotation phase shift will become a position-dependent phase shift, which I can detect by imaging the cloud. So what we're going to do in this experiment is image the cloud and look for spatial variations in the transition probability. what I should see is a spatial fringe pattern where the spacing of the fringes tells me about the magnitude of the rotation rate, and the orientation of the fringes tells me about the direction of the rotation rate. Then the overall phase tells me about the acceleration. So this technique was first described in this paper from Markasevich's group, where they gave it this, I think, very brilliant descriptive name, point source interferometry. Now I'd like to tell you a little bit about our experiment. So we have a relatively simple, I actually think the simplest cold atom atomic gyroscope that's been demonstrated so far. The idea is we make a magneto-optical trap to make a small cloud of laser-cooled atoms, and then we drop it, and as the atoms fall, we do this sequence of interferometer pulses, and then finally we image the cloud. And an important point in our experiment is that we image the plane that's transverse to the Raman axis. So in this plane, the orientation of the spatial fringes tells you about the two components of the rotation vector. And here on the right, I've got a picture of our experimental apparatus, and you can see that although the interferometer region is very compact, the actual experiment is not. There's a lot of work that you would have to do if you wanted to go and take this system outside of a lab. The final point I want to make is that there's an interesting difference between our experiment and the experiment by Markasevich's group, which is that their experiment was done in the 10-meter tower where they have this tremendously long interrogation time. And so their cloud expanded by about a factor of 30. In our case, we have a very short interrogation time that's constrained by this free fall. And so our cloud, we realized pretty early on, was only going to expand by about a factor of 3 or a factor of 5. And one of the things we were worried about is, are you still going to be able to see spatial fringes? Are the correlations between position and velocity strong enough that this technique still works, even in this small expansion regime? And I guess I wouldn't be standing up here telling you about it if it didn't work. So here's a slide where I've got some examples of the fringe patterns we're able to generate in this experiment. First, though, I want to tell you about the experimental sequence that we use. First, we load a magneto-optical trap. We do some optical molasses to get down to a temperature of a few microkelvin. We prepare the atoms in the state that we want, and then we do our interferometer sequence. Finally, we image the cloud. So if I don't apply a rotation, I can do the usual thing in atom interferometry where I measure the average transition probability in the cloud. So here what I'm showing you is the average transition probability as a function of the interferometer phase, which I'm controlling by scanning the chirp rate between my Raman lasers. If I do apply a rotation, that's when this spatial detection starts to get interesting. You can see here I've got two examples of spatial fringe patterns. And the red on this color map means most of the atoms are in F equal 2, and the blue on this color map means most of the atoms are in F equal 1. And you can see that I can detect both the magnitude and the direction of the rotation rate with these spatial fringe patterns. But one of the problems we ran into was that it can be very hard to tell exactly what the frequency of the spatial fringe pattern is, particularly in the case when there's less than a fringe across the cloud. And so we needed to come up with a trick for accurately extracting the frequency of these spatial fringes. And the idea is fairly simple. It's that every pixel in the cloud can be described by this form. Basically, every pixel in the cloud has an offset, an amplitude, and a phase. And what we'd like to do is isolate this interferometer phase. And the way we do that is by controlling the overall phase of the interferometer. And since I'm trying to estimate 3 quantities, it sort of makes sense that I need to take 3 images to do that. So in particular, if I jump the phase by pi over 2 between each image, I get a set of images that look like this. And in each image, it's hard to say exactly what frequency my spatial fringe is. But if I combine them in the right way, I can get a plot of the interferometer phase as a function of position. And now I see that I've got a nice gradient in the interferometer phase. And all I have to do is identify the slope of this gradient. That's the frequency of my spatial fringe. Once you know how to measure the frequency of your spatial fringes, the obvious thing to do is to measure the frequency as a function of the rotation rate. And here I'm showing you how k, the spatial fringe frequency or the phase gradient, depends on the rotation rate. And you can see it increases basically linearly. But the puzzle, when we got these results, was that the slope of the relationship between k and omega was different than what we expected based on this simple point source model. And we're pretty sure now that this effect is due to the initial distribution of the atoms. And I really like this slide as a way of making that vivid. So this is a picture of my initial cloud compared to my final cloud. And you can see that the final cloud is significantly bigger. But for me, looking at this picture really brings it home that it's not appropriate to approximate this as a point source. The structure of the initial distribution is important. So we've developed a few different ways to think about these spatial fringes. One of the ways that I think gives a fairly intuitive account is to think about how the atoms are distributed in both position and velocity. Basically, we need to think about the phase space density of the cloud. So here I've got a simple 1D model in phase space where you're plotting the position on the horizontal axis and the velocity on the y-axis. And if I had a point source, all the atoms would be concentrated at a single position with a range of velocities. But when I have a cloud with a finite initial size, I get an extended blob, something like this. And now you need to think about what cloud expansion looks like in phase space. Basically, the atoms in the upper half of the plane are going to go to the right, and the atoms in the lower half of the plane are going to go to the left. And so I get this kind of sheared phase space blob. And there's a few things to notice about this blob. Probably the first thing you notice is this correlation between position and velocity is no longer perfect. I have a range of velocities at every position, and that's going to lead to a loss of fringe contrast. Something that's a little bit more subtle is to compare the average velocity I get with my extended blob to what I would see if I had a point source. I think if you look on the edges of the cloud, it's pretty clear that the average velocity for my extended distribution is different than it would be if I had a point source. And that's going to lead to this shift in the average spatial fringe frequency. So this is another way of looking at it. Here what I've done is drawn the interferometer phase distributed on my edges of the phase space blob. Basically, I plotted the region where the phase space density is bigger than a certain threshold. And because the interferometer phase depends on velocity, it forms horizontal stripes in phase space. But my detection method is only sensitive to the atom's position. So I have to average over velocities and project this distribution onto the horizontal axis. So you can see a couple things. First, I have to average over several different phase shifts. That's going to lead to a loss of contrast. The second thing is that you can see that the phase I get on the edge of the cloud is different than the phase I would expect for a point source. And that's, again, leading to this shift in the spatial fringe frequency. So I've so far talked mostly in terms of intuitive pictures, but one of the nice parts about this formalism is that it maps in a straightforward way onto integrals and calculations. And there's a particularly nice case that we've been studying where the cloud has a Gaussian initial density profile. And there you can actually do all the math and get a closed form solution. And one of the things that comes out of that solution is that the key parameter in these experiments is the expansion factor. It's the ratio of the final cloud size to the initial cloud size. And in particular, you can show that with a Gaussian initial cloud, you expect the relationship between k and omega to be linear with a scale factor that's proportional to the point source scale factor, but it's modified by this term, which goes to 0. This term goes to 1 as the expansion factor gets very large, and this term goes to 0. Now I'd like to tell you about some of the experiments we've done to test our understanding of this picture. The first experiment I want to describe is what happens when you keep the interferometer parameters the same. You have the same interaction time and the same rotation rate, but you vary the total expansion time of the cloud. Basically, all I'm doing is adding time delays between the interferometer and the imaging stages of my experiment. And as you do that, you can see a few interesting things happen. The first thing you probably notice is that the spatial fringe frequency is decreasing. And that's just because we have a velocity-dependent phase shift. Basically, what's happening is the atoms with the biggest phase shift are moving further away from the origin, and the phase gradient goes down. But the more interesting thing is that as I go to longer expansion times, I get closer to the point source limit because the correlations between position and velocity are building up. You can also see that the fringe contrast rises as a function of the expansion time, which again is what you expect as these correlations between position and velocity build up. I should have to average over a smaller range of phase shifts, and I should get more fringe contrast. We've also done these measurements where we measure the scale factor, k, the slope of the relationship between k and omega, as a function of the cloud size. So here I have plots for 4 different clouds with 4 different initial sizes, and you can see that as the cloud size gets bigger, the the scale factor gets smaller, which is exactly what we expect based on the model that I've described so far. The last experiment I want to describe is what happens when we change the interferometer time. So we change the total expansion time, and that means we're going to change the expansion factors. So here what I've done is plotted the scale factor that we measure relative to the point source limit as a function of this expansion factor. And you can see we get a very nice trend where as the expansion factor increases, the scale factor that I measure moves closer to the point source limit. And this solid black line is what I would expect if this Gaussian density distribution model were exact, or if all of my density distributions were Gaussian. So we see some significant deviations from the Gaussian cloud model, and that's not exactly surprising because our clouds show significantly non-Gaussian shapes. So to wrap up the talk, I think the main conclusions that we can draw from our work so far are that you can see these spatial fringes even in the regime where the cloud has expanded by about a factor of 2. We are still optimistic that you can get interesting sensitivities, sort of navigation grade sensitivities, with this single atom source setup. But one of the main conclusions that comes out of this work is you're going to have to pay careful attention to these finite size effects. To get navigation grade scale factor stability, you want part per million scale factor stability. And that means you're going to have to come up with a strategy where these effects are controlled at that level. So what we're doing in the near future is trying to quantify the sensitivity and stability of our experiment. And we're starting to think about what does the next version of this experiment look like. That's all I've got to say. So thank you, and I'll take questions.